Hi, I'm Stefan Alfredsson, and in this video I will show you how to perform latency measurements in a practical exercise. And the purpose of this is to get hands-on training with theoretical topics that you have learned otherwise in the course, and see the effects of buffer bloat when excessive queuing occurs, and different mitigation techniques that we have when we can change the queuing discipline. So the goal is to do the exercise and be able to quantify the amount of buffer bloat that can occur and visualize this in different ways to improve the understanding of this topic. So to perform this exercise, we are using an emulated environment. It's called Mininet. And Mininet runs on the Linux. And if you already have a Linux installation, you can use that. If you don't have Linux, if you have Windows or Mac, we provide a virtual machine that you can use. So for this, we are using the Virtualbox software. And then we provide image 4 GB download complete with everything packaged. And along with this, we also have a repository with the experiment script files that you will use to set up the emulation environment, which I will walk through shortly. You can also apply the configurations that you learn here on your own systems if you have servers or directly connected clients running Linux. But due to the complexity of network connectivity, the results may not be as clear as in the emulated environment. In some cases, you will get very good benefit, and in some cases, it will not be noticeable, depending on where the bottleneck of your network connection is, basically. The network topology that we will study is quite simple. So we have two hosts, H1 and H2, and these are connected with a switch in this emulated environment. And the capacity of this network is 10 megabits, and then we have a latency of 10 milliseconds. So let's move to a live demonstration and see how we do this. In the slide material, you will have some screenshots if you don't follow along. So basically, we clone the Git repository, start Mininet, and then you open up a few more terminals. So here we have the window 1, where you start a ping process. In window 2, you set the queuing discipline, and then in node 2, you start a net server, and then you start a net perf and do the initial experiments, and then you will move on and do measurements using the Flint tool. So the first thing is to get Virtualbox. So just go to virtualbox.org and you will find this version. So you may already have Virtualbox, a previous version, maybe 5 or something like that. I did some initial testing and there seemed to be some problems with importing the virtual machine. So please, if you have those problems, upgrade to the latest version, to version 6. And you see that it's available for Windows, for Mac, and also for Linux and Solaris. So after you download and install this software, you can download the image that we are providing. So you see the URL here. It's also provided in the slide material and linked otherwise from the course homepage. So you download this, or if there is a more recent published virtual machine, please download that. I will put the old ones in the old directory for reference, but the latest one will be in this directory. There is also the Git repository with the files. So you have the URL here. So you can pause the video and go there, or you can find the link also in the course homepage and in the slide material. So here you have basically a README file, which contains the instructions how to perform these measurements, how to do the setup. If you're already having Linux, you have the command, Debian command, to install the required software, and then some instructions how to perform the experiments, which is what I will walk you through here. In this repository, you also have some scripts, the main run script, and you have a Python script to set up Mininet, and there is a traffic control script to set the different queuing disciplines. So you download the image, and then you import the appliance that you have downloaded, and then you will end up with a machine here. It may be, depending on which virtualization software you're using, it should be compatible with also other popular virtualization engines. You may need to adjust some of the settings of the virtual machine. So, for example, this display, you can change the scaling factor. Depending on your display, you may want to zoom it a little bit, especially if you have a high resolution display, for example, newer Macs or 4K display. This will make the fonts a bit more easier to read. In some cases, you may also want to enable or disable 3D acceleration. I have seen some problems with the display in certain settings. And then you start the virtual machine. And here we have the virtual machine. So regarding this scaling, it should also be possible to have auto-adjust the window size or auto-resize it, and then you should be able to drag and drop. Sometimes there have been some problems with this resizing, so you can use the scaling option, or you should be able to use this drag and drop. So here we have the first terminal, W1, and you can resize this one using Control plus and Control minus, and you can have different font sizes. And from here we will open a new window. So we'll have 2 of these. So this is window 2. So it may be that we already have some downloaded code from the Git repository. So remove that first, rm-rf dvad60. And then we will clone the repository into this directory. So this is just the URL that I visited. And then we have all the files in this directory, so change into that. And according to the instructions, the first thing to do is execute this run script as root. So we run sudo run sh. So now Mininet has started. In the other window, we will use this to configure the various queuing disciplines. So I have made a helper script to set the queuing discipline. And what this does is basically first delete any queuing discipline configured, and then add a token bucket that will provide some rate shaping, and this is used to shift the bottleneck from the network into the host where we can control the queue. And then we add the queuing discipline of our choice. For example, the FIFO or the codel or fq-codel or any other thing that you want to do. And this you can use on your own host as well to configure different queuing if you are testing it in a live network. So the first one that we want to test is the P5 fast, and this is the default queuing mechanism in Linux. And let's move back to the Mininet. And here we will start 2 terminals, H1 and H2. So this corresponds then to physical machines, if you would. In this case, they are emulated, but from the experiment perspective, these are communicating from node H1 to node H2. And they have the IP addresses 10.001 and 10.002. So for example, in host 1, we can ping 10.002, and we see that we have some 10 millisecond round trip time. So on host 2, we will start the measurement responder, and this is called the net server. So -d just says to put it in foreground mode so we can abort it easily. So we can move that window away so we don't need it anymore. Then in this first window, we can execute the command host1 ping host h2. So now we will have a continuous latency monitor, so to say. So we see that we still have this 10 millisecond round trip time. Now on the host 1, we will execute our first throughput measurement to have some bulk data transmitted. So let's run netperf capital H dash capital H 10002. And this then establishes a TCP session with the other host and then transmit bulk data, which will fill up the buffers. And you can see already here, we are going from 10 millisecond up to 1000, 2000, and then going back down to 10 millisecond again after the experiment has concluded. So here we were executing for 14 seconds and we achieved 3.87 megabit per second. So now let's try another queuing discipline. So now we use the P5 fast. If we instead would use codel, look at the ping time, and then run the netperf again. So now we see that we have 10 moving up to 30, 25, 32, 24, something like that. And comparing this to the 1000, 2000 millisecond round trip time that we had just recently, this is a huge improvement, of course. And finally, let's try the fq-codel. Configure that, and then run the netperf again, and look at the queuing time. So we have 10 millisecond, and we are barely adding any latency on top of that. We can also observe that we are achieving roughly the same throughput. So this is very interesting. Even though that we have reduced the buffer bloat to basically nothing, we are still achieving the same throughput, and that is one of the goals with these algorithms, to reduce the queuing delay while keeping a good throughput. So these were like getting to feel how it works. Now that we have a feeling how the different queuing disciplines interact, we will use a different tool to perform the measurement and store the data and be able to visualize it in another way. So we'll use a tool called FLENT, the Flexible Network Tester. So you can find it at, if you go to flent.org, you will find the description of this tool and how you can install it on your own host if you would like. So on the host 1, to do the Flent experiments, we first start with setting the queuing discipline. Let's start with the FIFO first. So we configure the FIFO, and at the host 1, we'll now execute the Flent tool. So it's Flent, and then we give it the name of the test. So it's RRUL, which is then real-time response under load, which is a pre-configured experiment scenario where multiple TCP streams are set up between the two hosts, and there is an download of data, upload of data, and meantime we send some ICMP packets and UDP packets and measure the latency that these packets experience. They are also using different priority markings. In our scenario, we don't do traffic differentiation, so they should achieve basically the same throughput and latency. If you are running in a real network, it may very well be that you have some traffic differentiation, and then this will be clearly evident from the packet traces. So you have the Flent tool, you have the RRUL test. There are different tests. Look at the web page and you can find those. And then you have the host 10002. And then we can have a text description of the test that we are doing. So when we look at these files, it's easier to know which queuing discipline we have been using. So in this case, we configured p5 for fast, and we can call this p5 for. And then we run the tool, and you have an expected runtime of 70 seconds. So during this runtime, there will be a period, a warm-up period, where the base latency is measured. After that, Flint will ramp up the TCP flows concurrent towards the net server at host 2. And then after some time, it will have a cool-off period where it will stop the TCP flows and wait for some seconds and see how the drop-off of the queuing is. So if you have no queuing, you will see the latency going back to the base latency. But if you have a lot of queuing, you will see that it will slowly taper off as the packets are drained in the queue. You can also see in the ping window at the same time that we have been experiencing a high delay of the ICMP packets, and then after the experiment finished, we are back down. After Flint is finished, we will get some statistics of the experiment overall, and we will also, if we list the directory, we will also have this file rrul with the timestamp and some information, which contains all the data. So you can look at this zles rrul, and it's basically a JSON file that you can parse if you would like to with some tool. To look at this data file, we can use the graphical user interface of Flint. So we use Flint --GUI rrul *gz. So if you have multiple experiments running, you will have multiple tabs showing up here. So in the first view, we have all scaled, which will show the download, upload, and the ping for the transmitted data. So here we have the different priority classes, and you have the average throughput. So of interest here is the latency, the bloating in this case. So we see that in the warm-up period, we have not 0, but we have 10 millisecond round-trip time, which you can see if you zoom in there. And then it ramps up to 1 second, 2 seconds, and then stabilizes around maybe 1700 milliseconds, 1.7 seconds. And then even after the transmission has stopped, we see that we still have a high latency while it drops off here as the queues are drained. So this is an example where we have a high amount of buffer bloat with the standard P5, and this is also the reason why this research was sparked when it was realized that all this buffering in the network was contributing to this excessive queuing delays. So the next steps is to then try out the other queuing disciplines. So set codel, and then run Flint again, codel, and then run it again with the fq-codel queuing discipline. And then you will see some quite differences in the latency, while the throughput should be fairly intact. So this will give you a hands-on experience on how the actual bloat happens and what you can do to mitigate this by setting various queuing disciplines. Thank you, and good luck with your experiments.